Pre-college, analyzing functions. Which graph represents a one-to-one function? Before we even get to the one-to-one aspect of this, let's discuss a little bit about functions in general. On a graph, how do you tell if a graph is a function? For function, we use the vertical line test. And so if we look at each of these, how many of them pass the vertical line test? So we see that A here, if I draw a vertical line anywhere on the graph, actually let me use a line tool, will be much neater. If we draw a vertical line anywhere on this graph, it will only cross the graph once. See, I could draw it here, it's only going to cross once, only crossing the graph once, so I'm fine with that. B, vertical line only crossing the graph once, so we're good. Oh, that was C. Let's check out B. See here, this time it is hitting the graph in two spots, 1, 2, so it is not a function. And to be a one-to-one function, you have to be first a function before you can even consider one-to-one. So you have to pass the vertical line test to be a function and a one-to-one function. We see that D only is hitting the graph once no matter where we put this. So A, C, and D are functions. Now how about one-to-one? Well, the vertical line test is for one-to-one. The horizontal line test is for, the vertical line test is for function. The horizontal line test is for one-to-one. And so it has to pass both the vertical and horizontal line test. We see the horizontal line test for here on A is hitting in more than one spot. So this is a function, but it is not one-to-one. We see for C, it passes the horizontal line test. No matter where I put this horizontal line, it's only hitting the graph once. And same thing with the vertical. So it's passing both vertical and horizontal line tests. That means, yes, it is a one-to-one function. And just while we're at it, let's analyze D. D, we said, passes the vertical line test, only hits once. But the horizontal line test, if I put the line directly over it, not only does it hit more than once, it hits every single time. So it definitely fails the horizontal line test. So C is our only option that passes both vertical and horizontal, so it is a one-to-one function. For a lot of function stuff, we're talking about keywords of domain and range. And if we remember, domain is all about the x minimum to x maximum, and our range is about the y's. So for this particular graph, we see that on the x-axis we're going from, let's see, that'd be -1, -2, -3, -4. This is -5. This is the leftmost the graph goes. Let me draw that a little bit better. A little out of practice, but yeah, this is as far left as the graph goes, and this is as far right as the graph goes, and that's 1, 2, 3, 4, 5, 6, 7, 8. So that means our domain, which we're going to use the symbol d of x, goes from -5, and x is our variable, our axis, from -5 to 8. And so that's how we're going to express the domain. And there's other ways to express it using interval notation and stuff like that, but we're not going to get into that right now in this video. The range, which we use our y value for, how low and how high does it go, is exactly that. How low and how high does this graph go? It does nothing to do with necessarily endpoints. It's just the lowest point on the graph is here, and this is at a value of -3, and the highest point on the graph is at +2. So our range goes from -3 and less than or equal to y less than or equal to 2. Now these are less than or equal to signs because they do go to those values. It does go to 2. It's not strictly below 2. The highest coordinate on this line has a y value of 2. So remember, domain x, range y. Now these next couple of questions are asking about domain and range, but they're not giving us graphs. They're giving us equations. This particular one, what is the domain of the function f of x is the square root of 3x plus 7. Now it's helpful sometimes to actually see the graphs of these. So what you could do is you could type into your calculator, remember f of x is the same thing as y equals, and so you could type into the y equals the square root of 3x plus 7 and get a visual, and sometimes that's very helpful for determining the domain and range. But we could do it algebraically because the domain is the x-axis, and it's all the values of x that it can be. And there's really two restrictions you're going to come across for this. For square roots, for square roots, I was going to say radicals, but that could cover cubed roots and so on. We're really only going to see square roots here. For square roots, what can't x be? Or what can't the square root be? And the issue is it can't be negative, because that's going to result in an imaginary number. And when we talk about domain and range, that's for real numbers. So what is the domain of real numbers? And sometimes that's how we phrase it. So basically, what are the restrictions on x, or what values of x are going to make this positive? What are going to make it real? So when you're asked for the domain of an equation that has a square root, basically you want to know what's going to make it positive, what's going to make it negative. And a good way to do that is to think about inside the radical, well, what's going to make it 0? Because if I know what's going to make it 0, I could pretty easily figure out what's going to make it negative and positive and so on. So you solve for what's inside the square root equal to 0. And that's going to give us 3x equals negative 7, x equals negative 7 over 3. And we see that we have a couple of answers here. This is negative 3 over 7, 3 over 7. This is our negative 7 over 3. This is positive 7 over 3, so that's not it. So by process of elimination, the answer is B. But let's talk a little bit why it is x is greater than or equal to negative 7 over 3. Because if we were to plug in negative 7 over 3 in for x here, that would result in this being 0. That's okay. You can have the square root of 0. Square root of 0 is 0. So that's okay. And if we plug anything larger than this, like 5, it's going to be 3 times 5, 15 plus 7. It's going to be irrational, but it's going to be real. It's going to be positive. That's okay also. So x can be negative 7 over 3 or larger. And that's what this is saying. X is greater than or equal to negative 7 over 3. These are all the numbers x can be for this to be real, meaning positive. Anything less than negative 7 over 3, like negative 10, that's going to result in a negative radical, an imaginary number, and that's our restriction. By the way, this little symbol right here, x with a slash, that's just the substitute of saying d of x dot dot. It's the same thing. It's saying x such that the x values have to be greater than or equal to negative 7 over 3. So for square roots, we can't have imaginary numbers in the domain. It can't be negative. For fractions, there's really only one restriction. A fraction simply can't be over 0. That's that concept of undefined. So the restriction, or what x can and cannot be, is basically x can be anything except for what's going to make the denominator 0. It's very similar to asking, what would make it undefined. And so looking at this concept right here, there's really only one number that would make this 0. If x were 1, we'd have 1 minus 1, which is 0, and 0 squared is 0. And so x cannot equal 1. And so we're going to say that the domain is everything except it can't be 1. And that's exactly what choice B here is saying, that x can't be 1. Greater than 1, like 5, sure. 5 minus 1 is 4 squared is 16. 1 over 16, that's fine. Less than 1, like even negative 1. Negative 1 minus 1, that would be negative 2, and it would square to positive 4. And we don't care if a fraction is positive or negative. It's real. I mean, negative numbers are real. It just can't be over 0. And so it just can't. It's every number except 1. This last example is asking about the range. And so remember, these are your y values. So f of x equals the absolute value of x minus 3 plus 2. Now, I actually don't have the calculator I could pull up here on this computer I'm working on right now, but let me just draw a little sketch. This would be, and we're going to get into shifts in a little bit, but the reason I could do this kind of in my head, because I know that this minus 3 means I would move absolute value. Well, hold on. Let me backtrack just 1 second here. And if you remember what an absolute value graph looks like, it is a V, like this. Now, I just want to, let's see if I'm going to be able to do this. I wanted to group these two things together to make this one graph. Just bear with me 1 second. So that's your standard absolute value graph. The minus inside of it means you actually go to the right 3, and the plus 2 means you're going to go up 2. And so the vertex of this absolute value, now again, if typing it into the calculator, you'll clearly see this. This would be at the point 3,2. And it just goes on and on. So the range has a minimum value. The lowest this graph goes is 2 on the y-axis and goes up to infinity because it just keeps going up and up and up. So the range would be basically 2 less than or equal to y less than infinity. Now, the reason why it's not less than or equal to, it's just strictly less than, is because you can never actually get to infinity. So that's why when infinity is involved, you don't have the equal to bar. But anyways, we see that that answer is not quite there because there's another way of expressing that, and that's on this part right here. This is the same thing as y is greater than or equal to 2. Greater than or equal to 2 implies 2 and up to infinity. And that's exactly what we see here. And if you type this into your calculator, you'll get that picture to really help you with that. All right, so we'll work on this stuff tomorrow in class. See you.